Hey everyone, welcome to a lesson on compound inequalities. In this video, I'll go over how to solve compound inequalities, how to graph them, and how to write their solutions using interval notation. I'll start off with some examples that use the word and. When solving these types of compound inequalities, we need to find solutions that work for both inequalities. Then I'll go over solving compound inequalities that use the word or. In these types of problems, we're looking for solutions that make either of the inequalities true. At the end, I'll go over one application word problem that'll hopefully help you understand what these inequalities could potentially represent. Let's get into it. In example 1, I'm going to start off by solving some compound inequalities that use the word and. In each of these four examples, we're looking for solutions that make both of the inequalities true. For this first example, let's start off with the inequality 6x minus 3 is less than 9. Our goal is going to be to isolate x to the left side here. To get x alone, I'll start off by adding 3 to the left side and adding 3 to the right side. Next, we're going to divide both sides by 6. 6 divided by 6 is going to be 1, so we're just left with x, and that's going to be less than 2, since 12 divided by 6 is 2. To satisfy this first inequality, x has to be less than 2. The second inequality we have here is 2x plus 7 is greater than or equal to 3. Again, let's isolate the x here. Let's subtract 7 on the left side and subtract 7 on the right side. 7 minus 7 is going to be 0, so we're left with 2x is greater than or equal to negative 4. Dividing both sides by positive 2, we're going to get x is greater than or equal to negative 2. Any values that are negative 2 or greater will satisfy this inequality. While there are values of x that satisfy this inequality on the left, and values of x that'll satisfy this inequality on the right, this problem is asking us to find the values of x that satisfy both of these inequalities. Let's graph these solutions on a number line. This less than sign tells us that we need an open circle on our number line. Here I drew an open circle on 2. I drew the arrow pointing to the left, pointing to all the solutions or the values of x that are less than 2. This greater than or equal symbol tells me that I need to have a closed circle on negative 2. X is allowed to be negative 2. Since x has to be greater than or equal to negative 2, I drew this green arrow going to the right towards numbers that are larger than it. Looking at the graph here, we can see that there are some numbers or solutions that work for both inequalities here. While the solutions for the purple inequality can go infinitely small, and the solutions for the green inequality can go infinitely big, only the values between negative 2 and 2 satisfy both inequalities. The filled in green circle indicates that x can be negative 2, and the open purple circle indicates that x is not allowed to equal 2. Whenever this is the case, we can take our solutions to our inequalities and write it as a double inequality. In this case, we're going to have negative 2 is less than or equal to x, which is less than 2. This left side represents the lower bound of the solutions, and this right side represents the upper bounds of the solutions. While this is one way of writing our solution, we could also write it using interval notation, writing bracket, negative 2, comma, positive 2, parentheses. The bracket is another way of representing the closed circle, and the parentheses is another way of representing the open circle. This notation is used more often in Algebra 2 and higher level courses. Let's try another one here. In this problem we have 3 times the quantity of 2x plus 5 is less than or equal to 18. Let's find out what values for x make this inequality true. Let's start off by distributing this 3 to the 2x and this 3 to the 5. 3 times 2x is going to be 6x, and 3 times 5 is going to be 15. This is still less than or equal to 18. We can subtract 15 on the left side and subtract 15 on the right side. When doing so, 15 minus 15 is 0, so we have 6x is less than 3. Dividing both sides by 6 here, 6 divided by 6 is 1, so we just have x is less than or equal to 1/2, since 3 divided by 6 is just 1/2. The values for x that make this inequality true are 1/2 or smaller. Now let's solve the second part of the compound inequality. Here we have 2 times the quantity of x minus 7 is less than or equal to negative 6. We can start off again by distributing this 2 to both the x and the negative 7. And 2 times x is going to be 2x, and 2 times negative 7 is going to be negative 14. And this is less than or equal to negative 6. I'm going to add 14 to the left side and add it to the right side. In doing so, the negative 14 and 14 cancel out to make 0, and we're left with 2x is less than or equal to 8. We're then going to divide the left side and the right side both by 2. 2 divided by 2 is 1, so we're just left with x is less than or equal to 4. Any value that is 4 or smaller will make this inequality true. This one will have a closed circle, as well as this one. For this purple inequality, I'm going to put a closed circle on 1/2 and draw an arrow to values that are smaller than it. For the green inequality, I'm going to put a closed circle on the 4 and also draw an arrow to the left. While values like 3 or 2 or 1 work for the green inequality, they don't work for the purple one. Remember that we're looking for values of x that are going to make both of these inequalities true. Any number that is 1/2 or smaller will actually satisfy both of these inequalities. Here we'll write our final solution as x is less than or equal to 1/2. Any value that is 1/2 or smaller will satisfy both of these inequalities. In interval notation, we can represent this as parentheses, negative infinity, comma, 1/2, with a bracket. Let's try another. Here we have 1/3 x minus 5 is greater than or equal to negative 3. I'm going to start off by adding 5 to both sides here to isolate the 1/3 x. Negative 5 plus 5 is 0, so we're just going to be left with 1/3 x is greater than or equal to positive 2. To get rid of this 1/3, I'm going to multiply the left side by 3 and the right side by 3, so we're just left with x is greater than or equal to 6. Any values that are 6 or greater are going to satisfy this inequality. Now for the second inequality. Here we have negative 4 times a quantity x minus 1 is greater than or equal to negative 2. Let's start by distributing this negative 4 to the x and to the negative 1. Negative 4 times x is going to be negative 4x, and negative 4 times negative 1 is going to be positive 4, and this is greater than or equal to negative 2. Subtracting 4 from both sides here, 4 minus 4 is going to be 0, so we'll be left with negative 4x is greater than or equal to negative 6. Dividing both sides by negative 4 here, negative 4 divided by negative 4 is just going to be 1, so we're left with 1x, and this is going to be less than or equal to positive 3 over 2. It's important to remember that when multiplying or dividing an inequality by a negative number, it's technically going to flip the inequality the other way. Make sure you pay attention to the change of inequalities here. Any values that are less than or equal to 3 over 2 will satisfy this inequality. Let's start off by putting a closed circle on 6 and drawing an arrow to the right. Then we'll put a closed circle on 3/2 or 1.5 and draw an arrow to the left. While there are infinitely many solutions that'll make this purple inequality true towards positive infinity, and infinitely many solutions that will make this green inequality true towards negative infinity, there are no values of x that are going to make both of these inequalities true. In this case, we're going to say that there is no solution. When you see the word and, you must find the range of solutions that make both of the inequalities true. In this case, it's not possible. Now let's try a double inequality. Here we have negative 4 is less than or equal to 3x minus 7, which is less than 8. When you see an inequality like this, we could separate it into two separate inequalities like we were doing earlier, but here I'm going to show you how to solve a double inequality right from the beginning. As usual, our goal here is going to be to isolate this x here. To start off, we're going to add 7 to get rid of this negative 7. With these double inequalities, whatever you do to any part, you must do to the other two parts as well. Adding 7 to all three parts of this inequality, negative 4 plus 7 is going to be 3, which is less than or equal to 3x. Negative 7 plus 7 is 0, and 8 plus 7 is going to be 15. Next, we're going to divide this middle part by 3, and we're going to do the same thing to the left and to the right side here. 3 divided by 3 is 1, is less than or equal to, 3x divided by 3 is just x, is less than, and 15 divided by 3 is 5. This represents the solution to our inequality. Any value that is bigger than or equal to 1, but less than 5, will make this compound inequality true. First, I'm going to put a closed circle on 1 and draw an arrow to the right. Then I'm going to put an open circle on 5 and draw an arrow to the left. Here we can see the overlap of the two arrows that let us know what makes both of them true. This would be our final graph. The interval notation here would be bracket 1, comma, 5, parentheses. In example 2, we're going to go over some compound inequalities that have the word or. In these types of problems, we're looking for the solutions or the values of x that make either of these inequalities true. The solutions for one of the inequalities doesn't have to be the solutions for the other inequality. In this first one, we have 5 minus 3x is less than or equal to negative 1. Let's solve this inequality by isolating the x. Let's start off by subtracting 5 on both sides of the inequality, And when we do that, we get 5 minus 5 is 0, so we're left with negative 3x is less than or equal to negative 6. Then we're going to divide the left side and the right side by negative 3. Negative 3x divided by negative 3 is going to be positive x, and this is going to be greater than or equal to positive 2. Make sure you pay attention to the inequality switch since we divided both sides by negative 3. This represents our solutions for the first inequality. Now we have 8 plus 2x is less than or equal to 5. Let's isolate this x here. We'll start by subtracting 8 from both sides of the inequality. When we do so, 8 minus 8 is going to be 0, and we're left with 2x is less than or equal to negative 3. Then we're going to divide both sides by positive 2, and 2 divided by 2 is going to be 1, so 1x is less than or equal to negative 3 halves. This represents the solutions to our second inequality. For the inequality on the left, we put a closed circle on 2. Then we draw an arrow to the right. For the inequality on the right, we put a closed circle on negative 3 over 2, or negative 1.5, and we draw an arrow to the left. It's totally okay that there's no overlapping in this compound inequality. Remember that in the original problem, we have the word or here instead of the word and. In these types of inequalities involving the word or, we're looking for the solutions that make either of these inequalities true. We can write our final solution as x is greater than or equal to 2, or x is less than or equal to negative 3 halves. Here we can write our final solution as x is less than or equal to negative 3 over 2, or x is greater than or equal to positive 2. This represents the solutions for x that make either inequality true. In interval notation, we can say parentheses, negative infinity, comma, negative 3 over 2, bracket, union, bracket, 2, comma, positive infinity. Let's try another. Here we have 1 minus 2x is less than or equal to negative 3. I'm going to subtract 1 from the left side and subtract 1 from the right side. In doing so, 1 minus 1 is going to be 0, and we're left with negative 2x is less than or equal to negative 4. Let's divide both sides by negative 2, because negative 2x divided by negative 2 is going to be positive 1x, or positive x, and we're going to flip the inequality to write greater than or equal to positive 2. Remember that dividing both sides by a negative will flip the inequality. This represents the solution to this inequality. Now let's solve the second inequality where we have 7 plus 3x is less than or equal to 4. We'll start off by subtracting 7 from both sides here. 7 minus 7 is going to be 0, so we're left with 3x is less than or equal to negative 3. Then we're going to divide both sides by 3 here. 3x divided by 3 is just going to be x is less than or equal to negative 1. Here's the solution to this inequality. Let's start off by putting a closed circle on 2, and drawing an arrow to the right, and putting a closed circle on negative 1, and drawing an arrow to the left. Our final solution here is going to be x is less than or equal to negative 1, or x is greater than or equal to positive 2. In interval notation, we can say parentheses, negative infinity, comma, negative 1, bracket, union, bracket, 2, comma, infinity. Let's try another. Here we have 3/4 x minus 3 is less than or equal to 3. We'll start off by adding 3 to both sides of this inequality. In doing so, negative 3 plus 3 is going to be 0, and we'll be left with 3/4 x is less than or equal to 6. To isolate x, we can multiply both sides of this inequality by 4/3. I'm doing this because the 3 and the 3 and the 4 and the 4 are going to cross cancel, and we're just left with x is less than or equal to. And on the right side, we can cross cancel this 3 and 6 to make 2 and 1, and we'll get an 8 on the right side. This is the solution to the first inequality. Then we have 1/2 times the quantity of x plus 10 is greater than or equal to 0. First, we're going to have to distribute this 1/2 to both of the x and the positive 10. 1/2 times x is just going to be 1/2 x, and 1/2 times 10 is going to be 5. 1/2 x plus 5 is going to be greater than or equal to 0. Then I'm going to subtract 5 from both sides of this inequality, and in doing so, 5 minus 5 is going to be 0, and I'll have 1/2 x is greater than or equal to negative 5. Finally, I'm going to multiply the left side by 2 and the right side by 2. By doing so, these 2's are going to cross cancel, and we're going to be left with 1x is greater than or equal to negative 10. Here's the solution to this inequality. I'm going to start off here by putting a closed circle on 8 and drawing an arrow to the left. Then I'm going to put a closed circle on negative 10 and draw an arrow to the right. It turns out there are infinitely many solutions that make this compound inequality true. There's no part of this graph that isn't covered by either of these inequalities. In interval notation, we write this as parentheses, negative infinity, comma, positive infinity, parentheses. And let's do another. Here we have 2/3 x minus 4 is less than or equal to 3. We'll start by adding 4 to both sides of this inequality, and negative 4 plus 4 is going to be 0, so we're left with 2/3 x is less than or equal to 7. Then we're going to multiply the left and the right side both by 3/2 to get rid of the 2/3. Everything's going to cross cancel here on the left side, and we're left with x is less than or equal to 21/2. We could also represent this using a mixed number and say x is less than or equal to 10.5. Either one of these is okay. Now let's solve our second part, which is 1/4 times a quantity of x plus 8 is greater than or equal to -1. We'll start by distributing this 1/4 to the x and to the 8. In doing so, 1/4 times x is just 1/4 x, and 1/4 times 8 is just going to be 2. This is going to be greater than or equal to -1. Next, we're going to subtract 2 from both sides of the inequality. 2 minus 2 is going to be 0, and we have 1/4 x is greater than or equal to -3. Then we're going to multiply both sides of the inequality by 4. Then we're going to multiply both sides of the inequality by 4. These 4's will cross cancel on the left side, and we'll have x is greater than or equal to -12. We'll start by putting a closed circle on 10.5 and drawing an arrow to the left. Then we'll put a closed circle on -12 and draw an arrow to the right. Similar to the last example, we have infinite solutions again. In interval notation, we have parentheses, negative infinity, comma, positive infinity, parentheses. Here in example 3, we have an application word problem. My goal is to help you understand how you can use all the algebra you were just practicing to solve a more realistic and understandable problem. Let's apply our understanding of compound inequalities to solve this problem. Eddie makes YouTube videos. After 2 weeks, he usually has between 480 and 560 views. He currently has 120 views and continues to get about 20 views per day. How many days would it take him to get to his usual amount of views? Is he on track or not? In 2 weeks, the number of views that Eddie typically has is between 480 and 560 views. Because it's between these two numbers, it can be represented with a compound inequality. Let's let x represent the number of days. Eddie already has 120 views and continues to get 20 views per day. We'd like to find out when he will have a minimum of 480 views and a maximum of 560 views. To solve this double inequality, we're going to subtract 120 from all three parts. 480 minus 120 is going to be 360 on the left, which is less than or equal to 20x, which is less than or equal to 440. Then we're going to divide the middle by 20 and do the same to the left and to the right. 360 divided by 20 is going to be 18, which is less than or equal to 20x divided by 20 is going to be x, which is less than or equal to 440 divided by 20 is going to be 22. The solution to this compound inequality tells us that if Eddie stays on track at his current rate, it will take him 18 to 22 days for him to reach his goal. Since 18 to 22 days is longer than 2 weeks, he's a little behind schedule. Make sure you like and subscribe to Eddie's channel to help him get those views. I hope you found this video useful in understanding compound inequalities a little bit better. Keep up the good work, and I'll see you in the next one.